So, couple quick announcements. And these are the same announcements we've had for the last couple days. So nothing special from this week so far. Once again, Canvas quiz right now should be open, due on this Friday. Midterm, just make sure that you've got that part booked off. So last class, we introduced you guys to Gabriel synthesis, and we started talking our way through enolates and aldol reactions. So this is where we're starting to make new carbon-carbon bonds, where we're generating the nucleophilic part of these carbonyl compounds we've been seeing. So aldehydes and ketones, primarily, we'll start there. By deprotonating those, you make enolates. Those enolates can now act as nucleophiles, where we're adding in things like electrophiles to do alkylation. And if we go to pi electrophiles, where basically the aldehyde or the ketone is both sides of that equation. Part of it is the nucleophile as the enolate, part of it is the electrophile as the carbonyl compound. So what is the major product if you did this reaction you see here? Okay, let's work this out. All right, step one. What's the question asking you? In your own words. The question is asking you to predict the product, right? You've got reaction conditions, you've got a starting material. Notice these things have had to give it a role. Sodium hydride is what? What do we use it as? It's a base, right? This second step, methyl bromide, that's going to be my electrophile. If I'm starting this reaction with a base, I have a proton here, and I have two protons there. So the first thing we have to do is in that first step, we're making an enolate. We're making our nucleophile. If I treat sodium hydride, high temperature, with that molecule, pink or green, which one of those protons are we mostly going to select for? Pink. Why? Yeah, these conditions are rigged up to do thermodynamic deprotonation. Well, that's terrible. Let's draw it properly. Thermodynamic deprotonation to give you the more substituted enolate is what we're going to get. Now, there's a couple features of this. The more substituted enolate, that's our high temperature sodium hydride. More substituted enolate, that's the nucleophile we're going to be dealing with. If we have this nucleophile, one thing I want to point out, what's the substitution of that center? Monosubstituted or disubstituted? How many carbons? There's disubstituted. The carbon nucleophile, this center here, this middle carbon right here, has two other carbon substituents attaching to it. That's going to be fairly crowded. That's, again, thermodynamically, that makes sense, but this is fairly crowded. That's an important part because what we're doing next is we're adding in the electrophile. This nucleophile is already going to be a bit sterically congested. Alkylation is the only reaction we can use when we have these doubly substituted enolates. We'll talk about this as we go through. Aldol reactions and other components, you can do pi electrophiles as long as it's monosubstituted. The second you cross over to doubly substituted, the alkylation is basically the only move you have. I'm going to add other carbons to it. I have to do something like alkyl bromides, alkyl iodides. So this is my electrophile. That's my nucleophilic center. I am going to add this together. I'm going to regenerate my ketone. And I've added my methyl group in here. And it'll add from either the top or the bottom, right? This is a pi system. And you're going to add that methyl from either face, so you'll have a mixture of possible different stereoisomers. Okay. So today we're going to continue on our conversation for aldol reactions. We're going to introduce the condensation, what's called the mixed or crossed aldol, and also things we can do to get some selectivity. As soon as we start going through to anything else where there's more than one possible aldehyde or ketone in the system, you can make these really complicated mixtures, and there's ways of addressing that. That's what we bring up these other considerations like intramolecular reactions and what's called the Knoevenagel reaction. So from last time, remember, catalytic base, typically we use these conditions. Under catalytic base conditions, we're taking two molecules of my aldehyde, that's my target material. That target material is going to make both a nucleophile and the electrophile, and we refer to these ones as the donor, which is my nucleophile piece, and the acceptor, which is your electrophile piece. What I mean there is, under base conditions, one of these guys is going to get deprotonated. It will make your nucleophile, which will be the enolate. The electrophile, the acceptor, is going to be same molecule, just not deprotonated yet. So this is bringing together two fragments, the nucleophile and electrophile, to give you this now extended thing. The new bond we're forming between the two is between the alpha center of your enolate and the carbonyl of your acceptor. So that's the addition. When you set up for this addition, though, if you look at the product, your product is what's called a beta hydroxy ketone or beta hydroxyaldehyde. We are sitting here with, I've got as highlighted, one molecule of water that's really, really, really close to just simply being eliminated. We can do a further reaction. Aldol addition is the first one where we actually put the two carbons together. That gives us our beta hydroxyketone product or beta hydroxyaldehyde. But if under those reaction conditions with either still our catalytic acid or catalytic base, with time and heat, what you'll get is a further reaction called the aldol condensation. Now, why we use this one is it allows us to form an important product. This is our alpha-beta unsaturated system. This is where we are now introducing a double bond over here. Second thing, too, is because we've done that elimination of water, it helps us to sort of form or lock in that product. Remember, we talked about it in the after lecture. Aldol reactions under these conditions are reversible. If we're trying to drive it towards something like this, sometimes losing water from the system can help us to lock in or form that as a major product. So the condensation is the next extension in the system. And all we're doing there is it's an elimination. I have a proton. I have what it could be water. If I lose water effectively across that bond, I'm doing an elimination reaction to make this double bond. And what's useful about this double bond is it's actually in conjugation. So what makes this possible is that, yes, we're eliminating water, but we make a relatively stable double bond, which is conjugated to your carbonyl. It doesn't matter if you did the addition from either the aldehyde or the ketone. The product will always be what we call this alpha-beta unsaturated product, where we have double bond in resonance with each other. It's a relatively stabilized system because of that. Again, how we control it, heat and time. This is something where if we do the aldol addition, I don't need to do anything else besides heat it up and wait longer. You will do the aldol condensation product. So how do we carry this out? If we do the condensation product after heating this material with sodium hydroxide, so aqueous sodium hydroxide like this is where we would split this up and say, I've got my starting material. I'm going to have catalytic base. That's going to form one equivalent of my donor, the nucleophile, and I'm going to have one equivalent of my acceptor, so another molecule floating around. Since I've got nothing else in the system, it's a dimerization, two molecules of the same structure. When we do the addition, that's our normal alpha beta unsaturated system, and we're going to get the aldol. First is the aldol addition product. We've got our new bond here to our beta hydroxy aldehyde. And again, if you're trying to number this off, I have 1, 2, 3, 4 carbons here from the same 1, 2, 3, 4 carbons. So 1, 2, 3, and 4. Carbon 3 is my nucleophilic center over here. And from the other fragment, 1, 2, 3, 4, that's my carbonyl center over here. So we're just keeping track of where the regiochemistry actually is for where these structures are. That's the aldol addition product. If I want to get to the condensation product, what I need to do is lose water between carbon 3 up here and this OH down here. We're making a double bond, which is in conjugation with that carbonyl. So we go back to the alpha center, where we already have done that deprotonation, where we already did our addition. It's the one that we have now formed our new bond across, and we're losing the hydrogen here and that OH. So the condensation product, using the same sort of color scheme, will be my aldehyde, as we had before, a double bond now attaching the two pieces, and the carbon skeleton down here. Now geometry, you could get E or Z geometries from these particular ones. What's now, again, for the most part, draw the one that looks most stable in terms of the trans geometry is usually what we see as favored. What we're usually saying is that that group and that group from these two aldehyde additions will end up usually trans to each other, but it's not a critical part that we're going to focus on. There will be sort of stereochemical control, but that's usually a third-year concept we'll go into. So same thing, I'm going to ask you to go through this. Now notice, a compound like this, there may be possibilities of doing more than one addition, right? A molecule like this, we have equal additions to both sides. It's possible if you just kind of push this hard enough to get much larger structures. So visually, what you're doing here is you're doing this condensation conceptually. You're losing both of the protons from one alpha center from your nucleophile, and you're losing the oxygen from your electrophile. Your donor and acceptor come together in this way. So this structure, if you see this alpha beta unsaturated thing as a product, the way it got there is probably an aldol condensation. It looks a little bit, fragmented, but this is something that you should be able to look at, that you've got this dimerization offset, right? It's the aldehyde and the aldehyde offset by one carbon. The carbonyl of the acceptor has now become this carbon-carbon double bond. That's that replacement there, where I'm highlighting the atoms that are sort of core to the center. Now remember, this is under an exchange where there's, since it's a Bronsted acid or Bronsted base, those protons are under dynamic exchange, but the oxygen you're extruding is that oxygen from the electrophilic center. So how does the dehydration work? The acidic one sort of makes sense. This is something you guys have probably seen before. It looks like an SN1 kind of process. The base mechanism needs something that I want to focus on just a little bit. What's happening under these conditions is if I have a base like hydroxide in this system, remember what we're doing here to do this elimination is I've got to get rid of that oxygen, I've got to get rid of that hydrogen. It's setting yourself up for what looks like one of our illegal moves, right? I've got to somehow punch out OH, and we don't have a proton available. We can't protonate that alcohol to make it into a better leaving group. Under acidic conditions, that's our SN1 type system, where I could protonate here to turn that into a better leaving group for this overall part. What I'm trying to do here is take this structure, and I'm trying to turn it into double bond, our group down here. Right? So I'm trying to remove both that and that group. How this happens, under basic conditions, go after the acidic proton first. So if we've got hydroxide present in the system, deprotonating here to reform our enolate is our first move. So the enolate that we generate under these conditions, this is our first move as we go through this component. Now what we've done, again, the reason we're doing this is under basic conditions, I can deprotonate that alpha center, I can regenerate my product enolate. This is also how we get scrambling of E and Z as well. As remember that that alpha proton is acidic enough that making the enolate again is possible. Now remember, just one quick mention. What did I say about substitution pattern? This enolate here has carbon-carbon. It is a primary or secondary enolate? There's two. That's one of the things that's actually very valuable at this reaction. As long as I do the aldol addition, I can make this enolate. This is the enolate of the product. Because the enolate of the product now has two carbons branching to that one, it is not nucleophilic. I can't add another aldehyde to it. I will not do another aldol on that center. It's locked off. I could alkylate this. If I hit this thing with something like ethyl iodide, I could put an alkyl group on here, but this is one of the reasons why the aldol reaction has a bit of control. We do an enolate of my starting material, I do an aldol addition, the product enolate, this one here, because of that double substitution, will not undergo another addition of another aldehyde. It can deprotonate, but you're kind of stuck here. Once you've done this, since it can't do an addition, what I can do is what's called an E1CB reaction. Think of it as an elimination reaction where we're kicking out an enolate, or an alkoxide. All I have to do is down, over, and out. I'm using that O- to reform my carbonyl. In reforming that carbonyl, I'm taking the double bond between the alpha center and I'm shuttling it over by one. And by doing that, I'm ejecting out O-. So the product I get after this will now be my aldehyde reformed, double bond, R group, and hydroxide. Again, why is this possible? I started with a hydroxide catalytically, I made a new hydroxide, and I'm regenerating a hydroxide. Yes?
By that same logic, is it not possible to do this mechanism in one step, or when you deprotonate, you're making the double bond and that kicks off the hydroxide?
You mean just directly? Like, it's still two steps. So here, look at it this way. What I think, let me just draw what I think you're mentioning. Let me move that over there. You're saying, couldn't I take this and you want to go base, grab, boink, boink in one step? So why maybe not? Again, not too bad, right? This is just proton exchange between the two. It still takes a breath. What I mean is, if you're doing this step over here, the center right here, that's acidic enough that making an anion there is resonance stabilized. So you lose that proton, you make a carbanion. And what you're saying is, if I made the carbanion here, that is just the resonance isomer of that. They're basically the same thing. So pushing it back to the carbonyl and bringing it down versus leaving the anion on the alpha center, both are allowed. Yep. OH is not a good leaving group, but you at least started with OH. At least energetically, I'm on the same surface. I have a hydroxide. It's not a great leaving group, but I'm still allowed to, I'm starting with a hydroxide and I'm kicking off a hydroxide. All I'm saying there is it's not going to be super fast. Doing the elimination under acidic conditions will be kinetically quicker. This is still allowed because at least we've got a hydroxide we started off, and at least we're not trying to go from like a acetate to a hydroxide. I'm at least no worse off energetically because I'm at least got the same basin present. Make sense? You're right. In terms of acidity, most of the thing will probably sit right here waiting for that to happen, but it will still move forward to do the elimination. And really what's happening here is you've got energetically, I'm making a very stable extended system, so my product here is now resonance stabilized. Energetically, the overall system, we're going to a bit more of a stable place. If that makes sense. So this is your kind of overall process. And again, like I said, just generally, I probably wouldn't do the deprotonation and hydroxide in one overall step. Usually there's sort of a brief in between where there's an acid step and then the elimination between the two. It's an existence of this E1CB that you may have seen in 203 as well. The acid catalyzed one, like I said, this looks a lot more like what you guys have seen. This is the SN1 kind of process where protonation of that hydroxide is now more favorable. And again, because of what we've talked about before, this is probably something you guys have seen more generically, and practice this one after. So let's walk backwards. This is where the challenge of this comes in, is we're starting to do carbon skeleton rearrangements. We're starting with a simple structure, and because of this dimerization, we're looking something that's not immediately obvious anymore. By removing out big chunks of the molecule, it can sort of hide pieces of it. So if I had to look at this and say, what if this was the aldol condensation product, where did we start? How do we go backwards? So a molecule like this, first thing you have to do is focus on, if I have an aldehyde and I've got this double bond next to it, this alpha-beta unsaturated system is the hallmark for you did an aldol condensation, right? If you see this carbonyl, single bond, double bond, that's something that very likely came from some type of aldol condensation product. Now what that means is you can break into two fragments. There's this piece here, which will be your nucleophile, and you can tell that because the alpha center to this carbonyl is the one that is now attaching to something else. The nucleophile, whatever was the nucleophile, will remain or have that carbonyl still part of it. It was deprotonated, it made an enolate, and then the carbon bond formed. The electrophile is this carbon fragment here. It's on the other side of the bond where that center, this is your electrophile, this center here used to be the carbonyl. It's whatever was accepting that nucleophile to make this new carbon-carbon bond. It will originally be the aldol addition, which we then eliminate. Third part of this is this fragment here. That double bond used to have the hydrogen on one side, the OH on the other. The OH is on the electrophile side. The nucleophile contained the hydrogen. So you're adding actually water across that center if you're working backwards. So if we take this step by step, first off is figure out your major fragments, find your alpha-beta unsaturated system, the alpha center to the carbonyl, that's your nucleophile fragment, the carbon-carbon double bond, that's replacing where the carbonyl used to be on your electrophile. So the immediate next step, if I was just to add water to this system, then what you're actually looking at is carbonyl is still in place. I have my carbon-carbon bond. I have my electrophile fragment where the hydroxide remains on the electrophile and the hydrogen is on the nucleophile fragment. That's the aldol product that I would have had. All I'm doing is I'm hydrating the double bond, putting the oxygen from the water on the third carbon, the one distal to your alpha-beta unsaturated system. The hydrogen is the one that sits in between the carbonyl and the alcohol center. This is your beta-hydroxy aldehyde or beta-hydroxy ketone between the two. So that means going back to the starting material, I'm going to fragment this bond between the two. I would have, well, if we did it by enolate, it would be O minus, that would be my nucleophile, and the electrophilic fragment that I would be coming back from this one would just simply be that aldehyde, which means it's two molecules of that compound is really what this came back to. So walking backwards is probably one of the more challenging part of this. And again, why I'm focusing on it is this is one of those cases where we've completely reformed the carbon skeleton. It's harder to see it initially because we've got to go through two transformations to get back to where we came from in something like this. But usually the easiest thing to do is focus on those critical fragments, work back step by step, and you should be able to put them together. So likewise, take this one, work backwards to your starting material. Where did this one come from? Okay, so condensations, up until now, we're taking nucleophile and electrophile, donor acceptor. If we put those two fragments together, that's our condensation, and it's always driven because we're making this highly conjugated system. As a quick note, in a lot of cases, it's very difficult to stop at the aldol addition product, especially like, for example, something like this. If I'm making something that has a high degree of conjugation, stopping and holding that beta-hydroxy ketone can actually be pretty difficult. The condensation product is quite favored just because you are making this very stabilized, very conjugated system. But again, heat is how we usually control it. Low temperatures, usually if we're trying to freeze out and stop at the aldol, that's what we'll try to do. Longer time, higher temperatures, your condensation is inevitable. The next thing that we're looking at, though, is what happens if both the donor and acceptor are not the same molecule. So up until now, we've taken one molecule and we're dimerizing it. The donor and acceptor are just two forms of the same aldehyde. One of them gets deprotonated, one doesn't, and it's a symmetric dimer between the two. If these are not the same molecule, you can have what's called a crossed aldol. So that's like this. If I take two molecules, they're both aldehydes. Now you can get yourself set up for what we would in the business called a mix-mess. You have every possible combination that could happen here. Now again, you've got some degree of control, but look at this one for a second. If I start with these two molecules and I do nothing else to the system, if I just treat it with base, I have A and B, and if I put them together, there are 4 possible condensation products I could make. So what I mean is, I have 2 protons here, which means I could use that as both a donor and an acceptor. If I deprotonate that center, I'm making my enolates. As the aldehyde starting material, I could use it as an acceptor. Same thing here. I have 2 centers. That could be either a donor or an acceptor. If I put every one of these together, I get every permutation that's possible that looks like this. I can have A with A to make this condensation product, B with B, symmetric condensation product. These are the 2 that we'd normally make if I just didn't mix the 2. These are the 2 cross products, where what I'm getting is A with B and B with A between those. That's just the permutations based on numerical combinations. We also then have E and Z isomers as well. So this is a very bad day at the lab. You don't want to be doing this because there's nothing really inherently that's going to control what happens. If you take these 2 aldehydes plus base and just send it, you are making a giant mess. So generally, aldol condensation, what we call the cross condensation, is not something we use just willy-nilly. We have to use something else to actually try to control it. We have these 3 permutations. We have 3 ways to try and bring control back to these kind of cross condensations. Either you choose your reagents really carefully. If we choose the right donor and the right acceptor, you have the ability to limit which products can happen. It's possible to create a reaction where one of these is only an acceptor or basically only a donor, and then we can actually try to limit the system out. We'll talk about those in a second. The other thing we can do is sometimes base and temperature. Remember, the relative acidity of these centers means I can choose the right base with an acidic enough molecule to only favor nucleophilic or deprotonation. I can generate only the enolate that I want. The last one is this more control. This is where how I bring the whole molecule together, the order of addition is what we would say, is what gives us a bit more control of the actual system. We'll talk about that one in a second as well. So first category, I choose what I call obligate acceptors. I use molecules where if you look at these are all acceptors. They're all electrophiles. In fact, all of them are either aldehydes or ketones. Most of these guys, all these, right? These 3 are aldehydes, these 3 are ketones. But what's unique about them is they don't have alpha protons, which means I can treat them with base, nothing's going to happen. So if you look through the first 3, the alpha center here, this is fully blocked, no protons, no enolate is possible. Aromatic ring, nothing's possible. Aromatic ring, nothing's possible. These are systems which we call obligate acceptors because all they can do is act as an aldehyde acceptor. They can't make their own enolate. So these are ones where they're blocked and there is physically no alpha proton. Same thing here. Ketone, no alpha protons. Methyls, no alpha protons. What's going on here? Those kind of look like alpha protons, but they are not accessible because of Brett's rule. Remember, this one here, if I try to yank off that proton, to make the enolate, I'm actually taking an sp2 center in this strained bicycle. It's not possible to do that deprotonation. So all of these are not, I can't make enolates with them. They can never be donors. They're only acceptors. So this is why if I pair these guys in, their only job is to act as the electrophile of the system. That's the easiest way, is just choose the right fragment of how you do this decomposition. The second one is the order of addition. So if I had a flask, this is something I can do experimentally. If I took a flask, and remember to bring these two pieces together at low concentration, usually low temperature, what I can do is if I park the base down here, and I put an obligate acceptor also down in there, what I just did is I have the acceptor, it can't deprotonate, it's sitting there ready to go. And it's just sitting there waiting. It's lying in wait. This is basically sitting there for like an ambush. And now you take your donor, my other aldehyde, as I add it to the system, the second it gets added to the system, a little bit of this aldehyde hits this massive concentration of base, it's instantly deprotonated. As soon as it's deprotonated, we just did two things. This donor is no longer available to suddenly couple with itself. You turned it into the enolate. And when you turn it to the enolate, there's all this acceptor ready there to sort of pair it off. What we're doing here is by this addition sort of step, I'm artificially controlling the concentration of the two species to allow only the reaction I want to happen. So as an example, let's say in the bottom here I have an obligate acceptor. I chose something where the alpha center has no protons. I have only my methyls. This cannot make an enolate. At the bottom also, let's say I've got a whole bunch of sodium, let's use a stronger base, sodium hydride, floating around in there. Sodium hydride is looking at the acceptor. They can't do anything with each other. They're safe. There's no reaction. It's just ready to go. Then what I do up here is I dose in my donor. I dose in a molecule like this. Now, as I'm adding that aldehyde, the second that it gets added, drop by drop, it's converted very quickly to my enolate, which means this one, it never really is in solution. It's only in the syringe. The second it hits the flask, instantly deprotonated, and it's never going to find one of itself again. You can't do dimerization between my donor because it's only converted to my nucleophile. It's never going to be floating around acting as the electrophile. So this is a chemical or sort of a geographic way to control the system by just positioning what goes into which part and then stepping out kinetically to do this reaction stage by stage. I'm only going to get this donor acceptor, which means the only product I'm going to have here would be donor, new bond. Let's say it's going all the way to the condensation product, acceptor. That's the only one I could make instead of having every possible combination. Yeah? Pray. The main way you can here in terms of E and Z, it's under equilibrium control. So something like this, you'd have to go by geography. You're right. This is not something easily that you can do. So once again, choose your conditions properly. Nice thing is these alpha, beta, and saturated systems, we'll come back to this, they can be nucleophilically added and extracted. That elimination reaction is reversible, so we can actually use it for other things later on. So this is sort of staging, right? This is kind of like Schotten-Baumann, where if we choose our conditions properly, we can get one reaction to happen, not the other, just by keeping the bad stuff away from each other in that way. We've got one more way of doing it where we actually invert the two. So look what's happening here. Now, my donor is in the bottom with the base. My acceptor is added dropwise. So this is slightly different. This one you would do usually with a ridiculously strong base like LDA at low temperature. What I would do here is I would start out in the bottom where I have LDA only in solution. So the base is waiting there. If I've got all this base waiting there, what I can do is slowly add what I want to use as my donor. So I want to use, let's say, same donor. And if step one, I add that donor slowly to the system, what I'm doing is there's always a lot of LDA. There's only ever a little bit of my donor. The second that these two guys see each other, we make the enolate. We make the lithium enolate of the system from the LDA deprotonation. Again, what I'm doing here is I'm preventing a case where the donor and the donor in its aldehyde and its enolate form are ever present at the same time. If I use something like LDA, It's a very strong base. It's a very rapid deprotonation kinetically. If I slowly add that kind of purple donor to it, it only ever converts to my enolates. Once it's the enolate, it's not going to react with itself. Nucleophile can't react with nucleophile. So as long as I set that up, now what I have down here at the bottom is a solution of my donor ready to go. Now all I have to do is carefully bring in my acceptor. This would allow me to take maybe another molecule that may allow enolate formation. Right? This allows me, again, this is not perfect, but if I had to do it, this is how I would actually try to do it. I form my nucleophile through my LDA addition to make only a solution of my donor, the blue one at the bottom. Now I'm bringing in my acceptor. And if I go very slowly, very carefully, what I'm doing is I'm trying to favor the nucleophile. The blue one is going to attack only my green acceptor, and then the deprotonation elimination. So that's where I would be trying to make this is your final product, let's say. My donor, and then double bond, and the acceptor. FYI, this is still really, really hard. Yeah?
If we were in a lab, what would we consider low concentration for this?
Anything below sort of 0.1 molar, 100 millimolar below, not 1 molar. This is usually dilute at 0.1 or lower below that is usually. Yeah? Oh, good question, good question. I just screwed that up. I can't use aldehydes with LDA, so let's do this with ketones. I'll just put that methyl everywhere. Ta-da! No, good call. I'll block it off in some other way. I just realized I created a new problem because now we've got kinetic and thermodynamic. Oh my goodness. I'm going to make it bulky. There. Now it's a ketone that you have to deprotonate on that side. Secret of anything with organic chemistry. If it doesn't work, add more methyl groups. Okay, sorry. What I was doing here, I want this to be single side. I don't want to worry about kinetic and thermodynamic. I've got that proton. That makes this enolate. That's why I'm blocking off that side. And yeah, the comment was, don't use aldehydes with LDA. Remember, we talked about last time. LDA is a good nucleophile for our aldehydes. Strong bases like LDA, we'd be doing this only with ketones. But as I mentioned, this is just two conceptual ways where what we're trying to do is separate the reactivity chunk from the acid-base reaction. That's what the goal of these two pieces are. And as a quick mention too, this is really, really difficult. This is even something that if you pull this off, it's not, this is the best choice if this is the molecule you're trying to make. Jumping to the next one. So we have our obligate acceptors. Those are things that can't make enolates. Now we've got geographic control. That's where we're forming the base or the acid separately. Third one is choose a nucleophile that has a very, very, very acidic center. This is what we call the Canova-Nagel reaction. They're aldol-like just because we're not dealing with aldehydes anymore. That's why we're calling it this aldol-like. Here, the donors have much more acidic alpha protons because of the functional groups that we're using. And if you recognize these guys, that was the pKa's we introduced at last class. These are things like our nitroalkanes. These are things where you have two stabilizing groups on either side. Things like double carbonyls, double nitriles, or carbonyl nitrile systems. So really what we're doing here is we're targeting an alpha proton that is a lot more acidic than your normal aldehyde proton that you're dealing with. Remember, aldehyde protons, they're about 15, 18. These guys are down at around 8 to 10. So by giving the system a much more acidic proton, you're biasing it that you make the enolate from this acidic center instead of having to deal with some other one. So it allows us to sort of get to focus on these components. So if I have a molecule like this, I'm starting off with two different molecules, and I'm actually doing two things that help out here. One, I've got alpha centers, right? This, no alpha centers in the system. So what I've done here is I've done two things. I've chosen a molecule that's going to act as my enolate. That molecule has two activating groups, the two carbonyls. So it allows me to differentiate the green protons from the red ones. Green ones are going to be way more acidic. They're in between the two carbonyls, and any anion generated at those green protons will be doubly stabilized by both. Second, I'm choosing an electrophile, my acceptor, that will not form enolates. It has no alpha protons, so all it is an obligate acceptor. Now, if you use these reaction conditions, my base is what? What is that little squiggly looking dude? Above the arrow, that's called what? Triethylamine. These are way, way, way less basic than things like alkoxides. It's not like sodium hydride. I'm going to something that is a much more simple organic base, which gives me a lot of control. This is way easier to run. So under these conditions, first step here is going to be the enolate formation. And the enolate I'm generating here, you could draw it as this guy. And remember, there's three different resonance isomers of this. If I deprotonate in between, I'm going to have oxygen minus on one, oxygen minus on the other, and carbon in between, right? There's this resonance stabilization where the negative charge is actually between those 5 atoms. But this is the enolate that I generate. That's going to do an aldol addition to this guy, right? So that's going to make my alpha beta. I'm going to make my new bond, and I'm going to do my addition to my aldehyde. This is benzaldehyde, so I'm ending up adding to that center where the green bond is the new bond between those centers. That's what I did in the first step. What's the second step doing? Catalytic acid or base, heat, a little delta. What's it? Condensation reaction. I'm locking in the goodness. I just made my carbon-carbon bond. I want to make sure that this thing is stable. So second step right here, I am eliminating water to make a double bond in between the two and making this. And this is also one of those cases that, honestly, stopping here would be a massive challenge. If you look at that structure, the proton in between those two carbonyls is still very acidic. This last proton sitting right here is just waiting to be deprotonated, right? It's still very acidic, so that acid base, anything in there is quickly easy to remove it. Second, look at your product. Not only have you made an alpha-beta unsaturated system, have made something that's conjugated or stabilized this way, and this way, and this way. Like, this is a massive, happy, planar system. We've got so much resonance that connects the carbonyl all the way through to the aromatic ring. So energetics means that we're making a system like this very, very easily. This is quite favorable to make something like this. This is one of those reactions that I would give it to any first year, and if you cannot do this, I cannot speak to you again. This is a gimme. So we're asking you to go through the same thing here. Same points. Find your structures. Find your centers. Do your acid-base chemistry in that same point. Next, intramolecular. So we've gone through and we've controlled these different centers. We've done it through acid-base type chemistry. We've chosen different nucleophiles and different electrophiles to guide the chemistry. The last thing we can do is put both the donor and the acceptor on the same molecule. So what we're doing here is ring formation again. This is where we're forming something where the two sides of the system for the condensation are actually locked up in the same molecule. Now, because of that, you have a possibility of forming a lot of different possible rings. Remember, if we're saying a donor and an acceptor in the same molecule, that means that there's two carbonyls in there to begin with. If there's already two carbonyls, there's a whole bunch of different alpha centers that you could deprotonate. So this has a first on its surface. It looks like you're going to make a huge number of different possible combinations, because you're saying, if I have two carbonyls and a bunch of alpha centers, well, nucleophile, electrophile, every pairing and permutation looks like it's going to go nuts. Why this reaction works, and this is actually something that we use quite heavily, is because thermodynamics really helps us out. First is ring size. If you can make a 5 or 6 membered ring, you do, everything else is out of scope. So that's really good, as it actually limits the number of possibilities just by choosing molecules where 5 and 6 membered rings are are possible. Now, a lot of the substrates, if you look at it, that 5-6 membered ring target is the first thing that's going to tell you which product you're going to make. It's about counting where the nucleophile electrophile actually is going to be. The second is this. You have to have a molecule with 2 carbonyls, but if the molecule has an aldehyde and a ketone, the aldehyde will always be the electrophile. It will always be the acceptor. So if you've got a choice between those two, you use this rank order where number 1, look for your 5s and 6s. Second, look for ketone attacks aldehyde. After that, it gets really, really wacky. But let's look at a case like this. So here's a molecule, 2 ketones. I've got my green center and I've got my blue center. I could make a nucleophile at this one, the blue center here, or the green center here. And I've done it so that it's symmetric, so we could consider the same 2 properties at the other end of the molecule. The interior one is the green one, exterior is the blue. If you look at this and you count them off, I actually have from the blue center, if I made the nucleophile here, that would be carbon number 1, and it's attacking this guy over here, which means from the blue center, that's 1, 2, 3, 4, 5, 6, 7. Carbon, carbon, to stretch those 2 together gives me a 7-membered ring. Versus, from the green side, this is carbon number 1 in that case, still attacking that center. That's 1, 2, 3, 4, 5. The green cycle will work because it makes a 5-membered ring and a 5-membered condensation. That is going to be the product you get. Versus if you go the other side, enolate at the blue center, it makes a 7-membered ring, it will not be formed. This is the major role of selectivity you have in the point, is to find a molecule like this, find your 2 carbonyls, designate them as nucleophile and electrophile, and you're doing this test where the nucleophilic center, that's your carbon 1, carbonyl is your final one, count your ring sizes you're going to do between the 2, and that gives you your first degree of control of which one of the 2 you're going to form. All right, we will kick off from this point on Wednesday. You'll see you guys then.
Okay, for these problems, first of all, we're asked to do the aldol condensation product, heating this molecule with sodium hydroxide. So once again, it means we're using this as both the donor and the acceptor. So it's a dimerization reaction similar to what we've discussed. If we deprotonate this, and again, we've got 2 protons or 2 alpha centers. Let's say we went from the green center originally, we would make this enolate, then enolate can now add to another molecule like this to give us our addition product. I'm going to give myself a bit more space. Like this. And after the condensation, we will have a double bond where the carbonyl used to be. And we would get something like this. Now, there's still 2 more protons here. So if the reaction were to continue, let's say we still have this possible, you could potentially further do this condensation where we replace the other center as well. So I'm just going to move that down a little bit. Let's imagine we were to continue it, and it's possible that we could do one more addition, same thing, deprotonation and aldol condensation out here as well. So in a molecule like this, again, if we said there was a large excess of this material or extended heating, then maybe this would be the preferred product that we would sort of dictate. The main one I would want you to focus on is that the AB, or the dimerization between one of these and another carbonyl, at least that first addition, so this core structure here would absolutely be what you would have to identify. So looking at the mechanism of the acid catalyzed process, this is more similar to what we might have for, let's say, a SN1 type mechanism. This is a case where we might get OH2+. We've made the leaving group into a much better leaving group. We have our R center and we have our proton. Here, then our solvent, let's say it was in an alcohol, can act as our base, and now we get a concerted elimination to give us our condensation product like this. Now, it follows more like the normal E2 elimination in a situation like this, where you'd have to have the anti-periplanar addition, or sort of the base deprotonation and group. That's typically how this would be looked at, but it's a far more straightforward one than the E1CB mechanism we show under base. So as we've discussed before, we're trying to find the two fragments that were used to make this molecule, and as I discussed in class, first thing we want to do is locate the carbonyl, alpha to the carbonyl. This fragment up top here is our nucleophilic fragment. Remember, for any aldol condensation product, there will be this alpha beta unsaturated one. So this center here is the new carbon-carbon bond that we formed, making this center here our electrophilic center. That's where the carbonyl used to be. So fragmenting those out, I would have the aldehyde from the top compound, like so. Oh, I don't like my angles I drew there. Let me redraw that. Yeah, it's a little better. Like that. And on the bottom, this is where we have carbonyl at the electrophilic center, and similar structure like so, like that. So these are the two centers, or the two aldehydes we would have for this kind of a dimerization. Once again, how you do this decomposition is locate your alpha beta unsaturated system, this kind of chunk here. That's the bond you'd be fragmenting for your condensation reaction. All right, so if we're asked to draw all possible ones, now we're not going to worry about the EZ geometries, but what we can do is treat these as, let's say, cases where this is my nucleophile and then this is my electrophile. So we have two fragments and they both can be either role. So if this was the nucleophilic fragment with another molecule of the same, so same one again, adding after condensation, we would get following. So this is where the nucleophile can add here or here. It's symmetric, so both of them give the same kind of product. And in a one-to-one addition, we would get this one where it's, call it A with A to give you that structure. Next is the dimerization. Let's do B with B. So if this was to act as the nucleophilic fragment, again, double bond, and we're going to have the dimerization like this, where we're replacing that center with our double bond. So that would be our dimerization between two of the same fragment there. Now we have the two possible cross products. Let's say A was the nucleophile, and then B is our electrophile. We get something like this, and then so this is our AB, and then we can do the reciprocal, our BA product, where let's say this ketone was the nucleophilic fragment, and that's being bonded onto the acetone as our electrophilic fragment. So those are the possible combinations of our aldol condensation, and that's only the mono addition. You know, we do actually have more centers over here, so you could imagine that dimerization over there gives us one more in that sort of cases. Now each of these has different permutations because you actually have three possible things can add in. I won't draw those all out, but you can imagine instead of just AABB, we could have AAA, AAB, A, B, 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 A, B, A, B, 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 A, and B, B, B. So that is a huge number of mass, and that's we're saying if we were bringing three compounds together where the residual, this residual center here or here could potentially couple again, so that one other permutation gives us a massive number of possible products. Okay, so if we're going to draw a Canova-Nagel reaction here. This is a very exothermic reaction to give you condensation product. And you can see why the stability of what we're forming here is actually very high. So we start off here. This fragment is our only alpha protons. We have no alpha protons over here. So this is our acceptor, or this is our electrophile, and it makes this our nucleophilic fragment. Now, putting those two pieces together, we're going to get, I'm going to draw it this way, the nitrile like this, and double bond onto the electrophilic fragment like that. And again, you look at this, this is a very highly stabilized ring. We have a lot of conjugation in this, so the condensation product is very likely. And I've drawn it specifically with this as the anti-geometry between these two rings. You can imagine that the other regioisomer is also possible. Okay, so now we're going to do ring formation based on what we mentioned before. So, as I mentioned, for any of these intramolecular reactions, you're going to have two carbonyls. Those carbonyls are going to have two possible centers. So here at this blue center versus pink, and then likewise, we've got red, and we've got, let's say, green. And any one of the centers I've indicated could be my nucleophile, making the other center the electrophile. So let's start here. If this blue center was my nucleophile, this would be my electrophilic center. That would be a 1, 2, 3, 4, 5-membered ring. So that's possible. Now, at least in terms of ring size, it's possible. We'll show you at the end of it. That is a little bit unlikely. We'll come back to that one in just a second. So that's allowed, let's say. However, if we do the other, this center being my nucleophile, that's my electrophile, that's only 1, 2, 3. That is not allowed. So we're going to take that one off the table as a possible. Likewise, from the red one, starting here is a nucleophile, 2 and 3, electrophile, that is also not possible. Those ring sizes are too small. So now what we have is from the green, 1, 2, 3, 4, 5, and from the blue, 1, 2, 3, 4, 5. And of these two, the green is going to win. So let me try that one first. Let me draw you both of those two structures, and then you can see what's happening. So let's do this compound. So first, we're making a 5-membered ring. So I'm going to start off with a 5-membered ring like so, double bond. This is carbon number 2, carbon number 1, and we're bonding carbon 1, 3, 4, and 5, where carbon 5 is this center right here. So that's the core structure based on this carbon skeleton that I indicated over here. The new bond is between carbon number 1 and carbon number 5. Okay, so now let's fill in the rest of the fragments. If you notice here, carbon 4 and 5 is they're shared as part of a 6-membered ring. So we're going to attach it on like that. Okay, carbon 3 has a methyl group attached to it, so we're attaching that piece onto it. Carbon 2 is our carbonyl, like we've seen. Carbon 1 has a methyl group attaching. So that's the structure we would get from that sort of green cyclization. Remember how we do this in stages: identify the nucleophile, identify the electrophile, count the carbon chain that's going to make it up, and then do the substitution pattern to kind of match atom for atom. If we did the same thing with, let's say, the blue one. So once again, 1 here, 2, 3, 4, and 5. Once again, that's the center we're adding into. And carbon number 1 is this one out here. So it's still a 5-membered ring. So I'm going to start with my 5-membered template. I'm going to say that's 1, 2, 3, 4, 3, 4, and 5. Likewise, new bond between carbons 1 and carbon 5. That's what we structured. Now let's fill in the pieces. Carbon 5, oh, excuse me. Remember, the double bond is what we're forming. The condensation reaction is going to give you double bond between both. So apologies, that's the correct structure here. We have the alpha, beta unsaturated with double bond between 1 and 5. So likewise, double between 1 and 5 here. Okay, so carbon 1 to carbon 3 is actually part of a 6-membered ring. Let's add the other pieces. Carbon 4 has a methyl group. Carbon 5 is a ethyl group attaching to it, or like this. But the rest of the ring here, carbon 1 is part of this ring system which bridges from 1 to 4, which means we have something that kind of looks more like this. So this is a bicyclic ring system. And more importantly, it's a bicyclic ring system with this double bond forced in over here. If I tried to draw it in that kind of other perspective that we may have seen in other cases, I have a 3-membered bridge, I have a 2-membered bridge, and I have this bridge head over the top, right? So I've got this apex piece, a 3, and a 2. So what that would actually look like is 2 carbons, carbonyl bridge over the top, and then we have 2 carbons attaching to it, and then 1, 2, 3, back to this one. So it forms this bicyclic structure. Now there's nothing inherently wrong with just a bicyclic structure. It's a bit more strained, so it's a little harder to make. That's partly why this one here is favored, because we're not forming a bicyclic structure in this compound. More importantly though, look what happens right here. Let's say that's this front carbon. That means in the 5-membered ring, we actually have a double bond this way. So we have this cross-conjugated system here where we have, just like we've said before, that's Brett's rule, making a double bond at the center, this bridgehead one, is not allowed. So that's not going to form easily. So that's why the non-bicyclic structure, 5-membered ring, wins. So if we're working backwards, this is again an intramolecular aldol reaction. We can use the same principles we discussed before. Step 1, identify the alpha beta unsaturated system through here. This bond is the one we're going to cleave, making that carbon the carbonyl we have now transformed. So I'm going to open up across there. This is a 1, 2, 3, 4, 5, and 6-membered ring. We're breaking between carbons 1 and 6. So that would look like this. And I'm going to put a carbonyl back over here. It would be an aldehyde specifically. So just to redraw that, I'll draw it out this way. And if we number it off, let's say that's carbon 1, 2, 3, 4, 5, and carbon 6, where, as I mentioned, that's the center that we did this addition to across here. So this is a case where we make a 6-membered ring from carbon 1 to carbon 6, and we dehydrate.